Welcome to the Deep Dive, listeners. But today we have a little something special for you.
Yeah, it's a crossover episode.
That's right. We got the AI.Code.Cast crew joining us today.
It's going to be a good one.
Absolutely.
Yeah.
So as you know, when AI.Code.Cast drops in,
We've got to solve a problem.
we got to solve a problem, some kind of algorithmic challenge, and today is no different.
Yeah, so today's problem is searching for a specific number, or target number, you might say, in a sorted two-dimensional matrix.
The sorted two-dimensional matrix. Okay, so I'm already thinking spreadsheet in my head.
Yeah, exactly, like rows and columns of numbers. And the key here is that they're sorted.
Ah, okay, so like smallest to largest.
Smallest to largest, yeah, both across the rows and down the columns. And that sorted aspect is really what's going to allow us to explore all these different efficient search algorithms.
So if we just like completely ignore efficiency for a second and we're just handed this matrix and told, hey, find this number, what would we do?
Well, I mean, if we weren't thinking about efficiency, we could just like start at the top left corner.
Yeah.
And just scan like every single cell until we find the number.
Yeah, it's just like go one by one.
Yeah, like check every drawer in your house looking for a lost key. You're eventually going to find it.
Yeah.
But it could take a while.
Yeah, you'll get there eventually.
Yeah.
Yeah, this is what we would call in the biz the brute force approach.
Yeah, brute force.
It gets the job done.
Yeah.
But not very elegant.
Not very elegant.
Not scalable. So in coding terms, what we would say is this has a time complexity.
Yeah.
Of big O of m times n.
M times n, where m is the number of rows and n is the number of columns.
So basically, like, the time it takes is like directly proportional to how many cells are in there.
Exactly. The more cells you got, the longer it's going to take.
Okay, so, but the matrix is sorted.
Uh-huh.
Can we use that to our advantage somehow?
Definitely. Yeah, let's think back to like a simpler scenario, like just searching in a sorted array, like a single list of numbers.
Right.
We have a really powerful tool for that. It's called binary search.
Yeah, binary search. Yeah, I remember this one.
Yeah, you split the array in half and you discard the half that can't contain the target, and you keep doing that.
So we keep having it until we find it.
Exactly.
Okay, so that's super efficient, but it's for a one-dimensional array.
Right.
But each row in our matrix is sorted.
Huh.
Could we apply that same idea to each row?
Yeah, absolutely. You could treat each row as its own separate sorted array.
Okay.
And then just perform a binary search on each row.
So we go row by row, and we do a binary search on each row.
Yep. And that would definitely be faster than the brute force approach.
But what would the time complexity be for that?
So for that, it would be O of m log n, where m is still the number of rows because we're doing m binary searches.
Yeah.
But each of those binary searches takes logarithmic time with respect to the number of columns, which is n.
Okay, so it's still faster than just like the straight up O of m times n.
Oh, yeah, way faster.
Way faster.
Especially as the matrix gets larger.
Okay, but we're still doing like all these separate searches. Is there a way where we could use the fact that both the rows and the columns are sorted
That's a great question.
to like be even more efficient?
Yeah, that's a great question. And that's what's going to lead us to some even more elegant solutions.
Okay.
So here's a hint. Imagine you're standing like at a corner of the matrix, say like the top right corner. How could you use the fact that like everything below you is larger and everything to the left of you is smaller to kind of like guide your search?
Okay.
Think about that.
Interesting.
Yeah.
I'll have to think about that one.
Yeah, I'll let you ponder on that for a little bit.
Okay. All right.
So that's kind of the jumping off point for this really clever technique called the staircase search.
Staircase search. Okay.
Yeah.
Right. I'm intrigued. I'm ready to hear more about this.
All right, so picture this. You start at the top right corner of the matrix.
Okay, top right.
Okay, and you compare the number in that cell to your target number. If the current cell value is bigger than your target, you know for sure that everything below it in that column must also be bigger, right?
Yeah, because the columns are sorted.
Exactly, because the columns are sorted, so boom, you can eliminate a whole column in one step.
Wow, okay.
And what if the number in that top right cell is smaller than the target?
Well, then everything to the left must also be smaller because the rows are sorted.
Exactly.
So you can eliminate the entire row.
You got it. So with each comparison, we're either moving down a row, eliminating that row, or we're moving left a column, eliminating that column.
Like walking down some stairs.
It's like walking down a staircase, hence the name.
Okay, so I can see how this would be way more efficient than checking every cell or even doing like the binary search on each row. But can we visualize this with like an example?
Sure. Yeah, let's say
Let's say our target number is 20. And we have this matrix, and I'll just read it out row by row. So we have row 1, 1, 4, 7, 11, 15. Row 2, 2, 5, 8, 12, 19. Row 3, 3, 6, 9, 16, 22. Row 4, 10, 13, 14, 17, 24. And finally, row 5, 18, 21, 23, 26, 30.
Perfect. Okay, so we start at the top right, which is 15.
Wow.
15 is smaller than our target of 20, so we move down, eliminating that entire first row.
Okay.
Now we're at 19. 19 is still smaller than 20, so we move down, eliminating the second row.
Yeah, right.
Now we're at 22. 22 is bigger than 20, so we move left, eliminating the last column.
Oh.
And we just keep going like this, and very quickly we'll either find our target number or
Yeah.
we'll run out of rows and columns to check.
So we're only visiting each row or column at most one time.
At most once, yeah.
That's pretty cool.
Exactly.
What would the time complexity for this be?
So in the worst case scenario, you'd traverse the entire top row and then the entire last column or vice versa. So the time complexity of the staircase search is O of m plus n, where m is the number of rows and n is the number of columns.
Okay, so just to be clear, that is significantly faster than the other approaches we've talked about.
Yes, much faster. It's linear time complexity.
Linear time. Okay,
Yep.
amazing. We're like basically doing one pass through this matrix.
Yep, a single pass, strategically navigating.
Strategically navigating.
Using the sorted property.
This is pretty cool.
Eh,
It seems almost too easy,
I know, right?
but it works.
It does.
What about space complexity? Are we using any extra memory here?
That's the beauty of the staircase search. It's also very space efficient. We only need a couple of variables to keep track of our current position.
Okay.
That means the space complexity is O of 1, a constant amount of space, regardless of the size of the matrix.
So it's time efficient and space efficient.
Mm.
I like it. Are there any downsides to the staircase search?
Like all algorithms, there are trade-offs. So the staircase search really relies on the matrix being sorted in both rows and columns.
Of course, right.
If the data is not arranged that way, this method won't work.
Yeah, it's like trying to find a book in a library and assuming that they're all in alphabetical order when they're not.
Exactly.
Yeah. Okay, you mentioned earlier that there's like a variation to this staircase search where you can start from the bottom left corner.
Uh-huh.
Is that like the mirror image of what we just talked about?
It is, yeah. You start the bottom left and you apply the same logic, just with the movements reversed.
Yeah.
So if the current value is bigger than the target, you move up one row, and if it's smaller, you move right one column.
So instead of down and left, we're doing up and right.
Yep.
But why would we ever choose to start at the bottom left? Does it even matter?
In terms of time complexity, both approaches are equivalent.
Okay.
The choice might come down to personal preference or maybe some specific characteristic of your data, like if you have a reason to believe your target is more likely to be in the lower half of the matrix.
Oh, okay. So it's all about choosing a starting point based on like where you think it might be.
Yeah.
Interesting. Okay, so we've talked about brute force, we've talked about binary search on each row, and now the staircase search, top right, bottom left. We've covered it all.
Mm-hmm.
Are there any other like tricks up our sleeve for searching a sorted matrix?
There's one more intriguing approach that we haven't discussed yet.
Okay.
This one utilizes recursion and a divide and conquer strategy.
Ooh, recursion, always a crowd pleaser.
Yeah, it might be a bit more complex conceptually, but
Yeah.
it really beautifully demonstrates the power of breaking down a problem into smaller sub-problems.
Our AI.Code.Cast listeners, they love a good challenge. I'm sure the deep dive audience does too.
Yeah,
Bring on the recursion.
let's do it.
Welcome back to AI.Code.Cast on the deep dive, ready to conquer this recursive divide and conquer approach for searching our sorted matrix.
All right, so instead of jumping right into the matrix, imagine we have this massive physical map spread out in front of us,
Okay.
and we need to find a specific landmark.
Yeah.
We're not just going to like randomly start searching.
Definitely no.
We probably try to like narrow down the search area, maybe divide the map into sections.
Yeah, like fold it in half.
Yeah, and focus on like the most promising ones. And that's really the essence of the divide and conquer strategy.
So instead of searching the whole matrix at once, we break it down into smaller pieces.
Exactly. We're going to repeatedly divide the matrix into smaller submatrices and use that sorted property to determine which sections we can just ignore.
But how do we decide which ones to keep and which ones to toss out?
So we need to choose like a pivot element, a strategic point in the matrix.
Okay.
That gives us like the most information. Let's say we pick the middle element of the matrix as our pivot.
Okay, right in the middle.
Yep. And we compare this pivot to the target number.
Okay, so if our pivot is larger than the target, what can we conclude?
If the pivot's larger than the target, we know that everything in the bottom right quadrant of the matrix must also be larger.
Right, because it's sorted.
Exactly, because both the rows and the columns are sorted.
So we can eliminate a whole quadrant just like that.
Just like that one step, what if the pivot is smaller than the target number?
Then we could get rid of the top left quadrant.
Boom, you got it. We can eliminate the entire top left quadrant because all those values must be smaller.
This is cool. So we're like cutting the search space in half with every comparison.
Exactly. It's like you're folding the map in half every time.
And we're only focusing on the parts we need.
Precisely.
Okay, so this is where the recursion comes in.
Yes, this is where it gets fun.
Right.
So we apply this same divide and conquer logic to the remaining submatrices. So we keep dividing, comparing to the pivot, and discarding irrelevant sections until we either find the target number or we're left with like a tiny submatrix that we can just easily search.
So we're breaking it down, breaking it down, breaking it down.
Breaking it down.
Until we find what we need.
Until we find it.
Okay, I can see how this is like super powerful.
Yeah.
But it also sounds kind of complex to code.
Yeah, it's definitely a little trickier than the staircase search.
What about the time complexity, though?
So for a square matrix, the time complexity is O of n log n, where n is the size of one side of the square.
Okay, so this is faster than like the binary search on each row.
It is, yeah, especially when you're dealing with like really large matrices.
O of n log n. Very nice, very nice. But you know what they say about recursion?
Oh, what's that?
Sometimes it comes with a little extra baggage.
A little overhead.
A little overhead. What about the space complexity here?
Yeah, you're right. Recursion does use some extra space for like the function call stack.
Right.
So the space complexity for the divide and conquer approach is O of log n.
Which is still not bad. It's logarithmic.
It's not bad. It's logarithmic to the size of the matrix.
Okay, so a little more memory than the staircase search, but potentially much faster.
Potentially much faster, yeah.
Especially for large matrices.
Yeah.
Okay. Any downsides to this approach?
You're sensing a pattern here.
I think I am.
Yeah. So like the other efficient algorithms we've discussed, this only works if the matrix is sorted.
Yeah, okay.
If the matrix isn't sorted, we can't make those strategic discards and the whole thing falls apart.
If it's not sorted, you're basically back to brute force.
Pretty much, yeah.
All right, well, hey, we've covered a lot of ground today.
Yeah, we did.
We talked about brute force binary search on each row staircase search, and now the divide and conquer approach. It's amazing how this one little constraint, sorted data,
opens up a world of possibilities.
leads to so many different solutions. What's the big takeaway you want our listeners to remember from today?
I think the biggest takeaway is that understanding the characteristics of your data can unlock all these optimization opportunities. Like in this case, the sorted property allowed us to go from like a basic brute force solution to much more efficient algorithms.
Absolutely. It's not just about memorizing these algorithms. It's about understanding the problem and choosing the right approach.
Yeah, choosing the right tool for the job.
Now, before we wrap up, I have a challenge for our listeners.
Okay.
We've been talking about these 2D matrices, which are like nice and neat grids.
Yeah, like a spreadsheet.
Yeah, but what if our data was organized differently?
Ooh.
What if it was structured like a family tree, with branches and sub-branches, or even like a network of interconnected nodes?
Interesting.
Could we adapt any of these search strategies to those types of data structures?
That's a fantastic question. It's like a whole other world out there.
It is.
Of algorithms waiting to be explored.
Keep those coding brains engaged.
Yeah, keep thinking, keep coding.
Well, that's all the time we have for today's deep dive into searching sorted matrices. Thanks for joining us on AI.Code.Cast here on The Deep Dive. We hope you learned something new and, most importantly, had some fun along the way.
Happy coding, everyone.